7.20 is consider a rectangular fin that is used to cool a motorcycle engine. The fin is 0.1 meters long and at a temperature of 250 degrees Celsius, while the motorcycle is moving at 80 kilometers per hour in air and 27 degrees Celsius. The air is in parallel flow over both surfaces of the fin. Turbulent flow conditions may be assumed to exist throughout. Part A is, what is the rate of heat removal per unit width of the fin? All right, so we have a rectangular fin. And they tell us the length is 0.15 meters. We have the temperature of the fin is 250 degrees Celsius. So they're very much making an assumption here, or this fin is maybe copper or aluminum, so that they're able to say that the fin temperature is all uniform throughout. Okay, it's conducting through it and being the same temperature. As we know from chapter 3, there's a temperature profile of the fin. Okay, in this problem, they're just saying it's one temperature. The motorcycle is moving at a velocity of 80 kilometers per hour. So that's going to be our U infinity. We have 80 kilometers per hour. And T infinity is 27 degrees Celsius. So we have parallel flow. And they say it's turbulent. All right, so they want us to find the heat rate per unit length. So it's Q prime, which is Q divided by W. All right, so our schematic. We have our fin. All right, so we have U infinity, T infinity given. We have the surface temperature, which is the temperature of the film, or sorry, of the fin. Okay, and then we have our lengths. All right, and this is air. All right, so where do we start? You know, there's 14 people out there. Someone's got to have an idea. Where would you begin this problem? Not even thinking about chapter 7, new material.
Start with a COE.
Okay. All right, COE. It's a little better. All right, so we have energy in, out, generated, stored, right? So do we have any energy in this case? So if I make my boundary here, do we have any energy out?
Would it be yes because it's cooling?
Yeah, so it's cooling. So we got some convection leaving, right? Okay. Energy generated or energy stored? Let's cancel those, right? There's nothing generated inside of it. There's no energy. We can assume it's steady state. Okay. So we have cooling. Do we have energy in then? For cooling this and its steady state, where is this energy coming from? So we said it's a rectangular fin that is used to cool a motorcycle engine, right? So where is this heat that we're cooling, this convection, coming from? Because of right now, we just have heat out.
It'd be coming from the engine, correct?
Yeah. Yep. So then we would just have from our engine. Okay. All right. So what's coming from the engine is being lost in convection, right? So we have then Newton's law of cooling, right? So it's H bar because we're looking at the average, because we're looking at it for overall over this whole fin, not a single point. And so we know we're going to have to get that, but because that wasn't given. Surface area, we have some width times some length. We have surface minus, okay. So we're given this, we have length given, so we have to get our convection coefficient, and what do we do with the width? Or does this equation look right? Start there. Does that surface area look right? So I have a unit width times length, right? Am I cooling one side of the fin or two sides?
Both.
Yeah, so that's a common mistake I would see is forgetting this 2 in the front. Okay, so there's 2 widths times the length. Okay. And then the width, we go back to our what we're originally trying to solve. Right here, it's per unit width, right? So we get okay. All right, so now we need to figure out the convection coefficient. So where do we start to do that? what do you think your first step is in getting this convection coefficient?
The Nusselt number.
The Nusselt number, okay. All right, so Nusselt number. Since Nusselt number is average Nusselt number is H bar over H bar times L over K of the fluid. All right, we're looking for Nusselt number. We have L. We need the thermal conductivity of the fluid, right? So one thing with this is, do we think we get these fluid properties at the surface temperature or T infinity? Or some other value. So we're looking for thermal conductivity of the fluid, which is air. What temperature do we get it at?
The T infinity.
No, so it's not exactly that, because I posed the question this way on purpose, but let's say if we have, let's do it this way. Let's write it down here. If we have boundary layer, right? Here would be T infinity, here's T surface, and all throughout this is where all this important stuff is going on. So what we actually do is get it at what's called the film temperature. Okay. So TF, which is TS plus T infinity over 2. So this is also a common mistake that I see. So in this case, we have TS and T infinity, so we average it, and we get 412 Kelvin. So we get it at that. Which is 0.0346. Okay. Now we have to get the convection. So we're still looking for the convection coefficient. So we need to get our Nusselt number. So if we're now trying to find the Nusselt number and we're trying to find our equation for our Nusselt number, what do we think some of the main characteristics do we need to know to get the right equation for the Nusselt number? What do we? Oh, sorry. Go ahead.
Oh, I was going to say the critical Reynolds number.
So the Reynolds number, yeah. So we need to know Reynolds number, right? Because we're gonna want to know, laminar versus turbulent, right? So we want to get our Reynolds number, okay? Okay, in this case, we got U infinity, L. We need to grab this at 412, okay? And that's just ends up being 27.85 times 10 to the negative 6. All right, so I don't actually have it, but I didn't calculate this. It also told us it was turbulent, is one thing. Most problems don't, but we know we're going to get a value, and it's going to tell us typically whether it's laminar or turbulent. And in this case, it's going to say we're going to get a value that's turbulent. Okay. All right, so now we know we're turbulent. Anything else we would need to know to figure out the right equation? So another thing, maybe you're not even thinking about it because you already have the right idea of where right to go to it, but it's geometry. Okay, I'm just thinking bigger picture. So geometry. Okay, there'll be a different equation or set of equations for, in this case, we have a flat plate in parallel flow. So the relationship will look different depending upon the geometry, okay? And then another one is whether you want local convection coefficient or average, right? And we want H bar, so we want the average convection coefficient. All right, and we can go now with those understanding, we can go and find our right equation, or there's also a nice table, right, in the back of the chapter, table 7.7 has equations. So it has all the relationships, okay, for boundary layer thickness, friction coefficient, local Nusselt number, average Nusselt number for different geometries, different, laminar, turbulent, even geometries we didn't get to in the last section, like an impinging jet, a pack of bed of spheres, a falling droplet, so different ones there too. All right, so we go in there and we figure out we said we're turbulent, flat plate, parallel flow. We want the average, so the bar on it. Okay, so we can go grab our turbulent one. So it's turbulent throughout. So we get our equation 7.38. Okay. So we can get Reynolds number. Where do we get Prandtl number? Any ideas? So we also just get it at TF and go into our appendices. And we get 0.69. Okay, so now that's enough, and we start solving, right? So our Nusselt number comes out to be 378. So then we go back up. Now we can get our convection coefficient. It's 87. And now we can go back to our COE with Newton's law of cooling and plug it in and solve for our heat per unit length. And we get 58.26 watts per meter. Okay. Any questions? So most of this in chapter 7, and this is what you'll see, most of this is all the problems you've done before. They just are now asking you to solve and figure out your own convection coefficient. So right here, is all the new stuff, right? Everything else is all the stuff we've done before, okay? This is the new stuff, is just getting the convection coefficient. Okay. Questions?
Yes, so for our K and our Prandtl number, we have to find both of them at the T average of the fin and the air.
Yes. So they're all at the film, what's called the film temperature. Okay. Any other questions? All right. So let's do 7.36. Problem 7.36. A long cylindrical heating cylindrical electrical heating element of diameter D is 12 millimeters. The thermal conductivity K is 240 watts per meters Kelvin. Density is 2,700 kilograms per meters cubed, and specific heat CP is 900 joules per kilogram Kelvin. Is installed in a duct for which air moves in cross flow over the heater at a temperature and velocity of 30 degrees Celsius and 8 meters per second, respectively. Part A is neglecting radiation. Estimate the steady state surface temperature when per unit length of the heater, the electrical energy being dissipated at a rate of 1,000 watts per meter. And part B is if the heater is activated from an initial temperature of 30 degrees Celsius, estimate the time required for the surface temperature to come within 10 degrees of its steady state value. Okay. All right. So we have a long cylindrical heating element. We have a diameter 12 millimeters, which is 0.012 meters. We have thermal conductivity 240 watts per meters Kelvin. We have a density 2,700 kilograms per meters cubed. We have a CP of 900 joules per kilogram Kelvin. U infinity of 8 meters per second. It's cross flow. Actually, this should be capital D. It's cross flow. And then T infinity 30 degrees Celsius. All right. So they want us to find in part A, surface temperature, TS, for steady state, and it's going to be three things, all right? And for steady state, comma, P electric is 1,000 watts per meter, and neglect radiation. And then part B is estimate the time so we have a delta T when the initial temperature is 30 degrees Celsius and surface temperature to come within 10 degrees Celsius of the steady state. So that means so TS minus T steady state is 10 degrees. All right, so our schematic. All right, so here's our cylinder. Okay, and then we have our cross flow, right? And our diameter, okay. And there's electric power of 1,000. Okay. All right, so we have this long cylindrical heating element and has 1,000 watts per meters inside. And we have a lot of properties, dimensions. We have cross flow of with the velocity and the temperature of the fluid that's going to hit it. And they want for part A, the surface temperature. So our surface temperature, right, for steady state, right, neglecting radiation. So where do we begin?
COE?
Yep, so our COE, right? All right, so it's steady state, right? This one, so steady state. Do I have, we have energy in, energy out, energy generated. Is any one of those terms canceled? And which one? So we know we have this electric 1,000 watts per meter. Is that in, out, or generated?
The generator.
That's generated, right? And then the other thing we have said neglect radiation, but we're in the convection chapter, right? So we're going to have convection. Right? Let me make our boundary. So we got convection, right? So that means we have no energy in. we'll do it per unit length. All right, convection, we have Newton's law of cooling. It's over the whole cylinder, so it's H bar. The area is the outside area, right? So that'll be I D. Okay, the L is removed because it's per unit length, right? Okay, so that's why I have the L on, right? So then we have the surface temperature minus T infinity, right? So we go through this. We have diameter, we have T infinity. We do not have the surface temperature, H bar, we have P electric, okay? Okay, so we're gonna have to go some route there. So I'm gonna actually finish this next class, so I'll push off the homework for a day or two, even though I think the students in the past have done really well with chapter 7. But I'll still give you a little bit more time since we didn't get to finish this second example. Is there any questions you guys have, guys and gals?
No, I think not yet.
No? Okay. All right. There's no other questions, then that's it for today. And we'll continue, finish chapter 7. It won't be too long in the next class, and then we'll move on to chapter 8, which is internal flow. Okay.
Thank you.